Okay, so let's start. And good morning. And so I'm afraid some of you were not here yesterday. So can you log into the system? Okay. So do you have your user ID? Okay. 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 So let's continue the correctly communication part for the MPI. And so we have 4 problems now. Okay. So first we start for the dot product of the vectors. So this is a very important and also directly utilized for the parallelization of the finite element method. So conjugate gradient solvers. Okay, so first I'll start this part about some discussions about global data and local data. And yesterday, so we have already talked about discussed about the local data structures. So how do we number, okay, the local number for the distributed local files. But this one is a little bit more fundamental, okay? And the data structure of parallel computing based on SPMD, where large-scale global data is decomposed to the small pieces of local data. So this is a issue. And this is just a repeat, which I mentioned yesterday. So generally, PC with 1 GB memory can execute finite element applications with up to 1 million meshes. Okay? But if you think about the 1,000 kilometers square and 100 kilometer depth, it's corresponding to the Southwest Japan. So yeah, we are expecting the next very big earthquake in this area. And so you can see we need 100 millions of meshes, even if you apply the 1 kilometer cubed. So it's a very coarse meshes. Okay? And the large scale data is decomposed into the small domains, and the parallel and local operations are possible. But the global computations is done by the communication among domains. Okay. So we start from the large scale data, and we decompose into the local small data set. And we do the parallel computing, which is a local computing. But in order to keep the consistency with the original problem, we need some communications among these local part. And it is important to define proper local data structure for target computation and its algorithms. And so if you are from the, if you learn about some computer science, so you may have taken a class on algorithms and data structure, okay? And so from this point of view, so algorithms is equal to the data structures. And as I mentioned in the beginning of this class, so this is the main objective of this class, to define the proper local data structure. Okay. Okay, consider the dot product of the following Beck P and Beck S with length equal 20 by parallel computing using 4 processors. So actually, Beck P has all component is 2, and this one is all 3. And you can easily compute or calculate the dot product of this Beck P and Beck S. So you can see 2 by 3 is equal to 6, and we have 20 components, and the result is 120. Okay. But so let's think about doing this computation using 4 processes. Okay, so you go to the directory, so S1 directory, which I showed yesterday. So you can find .f and .c. So there, Fortran and C serial code. Okay, so using PC. Okay, so you can see the Beck P and Beck S are real double precision vector. The size is 20, And we just introduced 2 and 3 for each of the component of Beck P and Beck S. Then we calculate the dot product. Then we get the result for this sum. So what we are trying to do is parallelize this computation on the MPI. In order to do that, MPI reduce is a very convenient function for that. Okay? So MPI reduces values on all processes to a single value. Okay, sum, product, maximum or minimum, etc. Okay, and we have several arguments. The features of the MPI is that we have a lot of arguments, and we need to be careful about the configuration of these many arguments. Okay. Okay. So choice means that we have several types, and data type is that could be integer, single operation, double operation, or character. Okay, so anyway, so these are the name of the argument, and the next one is the type. Okay, and this one is I is the input and O is the output. Okay. Okay, so first one is a send buffer. Okay, and the starting address of the send buffer. And the next one is a receive buffer. Okay, it's a starting point, starting address of the receive buffer. Okay, and the type is defined by this data type. Okay, so yeah, like this MPI int, float, double, character for the case of the C. In the case of the floater, it's an integer, real, double operation, and character. Okay. And the next one, count. So this is an integer. It's a number of elements in send and receive buffer. Okay. And this is a data type. And the next one is the operation. Okay. So type is a MPI op. Okay. So this is a reduce operations. Maximum, minimum, sum, product, logical and etc. Okay. And the users can also define operations by themselves. So we can define our original operations by MPI OP create. But we skip this part today. And the root is the rank of the root process because so we can see the result is merged into a single process. Usually it's 0. Okay, and so root is a rank process, and the last one is a communicator. Okay. So these are the arguments. Okay, but if you are not so familiar with the MPI, so probably you are very confused. So what is send buffer and what is receive buffer? Well, you can understand the count, so number of the elements, data type, operations, and root and communicator. But probably you cannot understand what do send buffer and receive buffer mean. Okay, so arrays of sending buffer and receiving buffer often appear in MPI. And addresses of send buffer and receive buffer must be different. Okay. Okay. Okay, so this is a very typical case. It's A is scalar. Okay. And so this is a Fortran and this is C. So in the case of the Fortran, so some error code is included. In the case of the C, so value of this function itself is some error code. Okay, so if A is a scalar, so this count is usually 1 because we are sending just one component. And if so A is some array, for example, we can send 3 components. And what does starting address of send buffer mean? Okay? So if you write, so A, in the case of the Fortran, A1 is a starting point, and A0 is a starting address. Okay, and this means three continuous components of A1 to A3 or A0 to A2 are sent. Okay, if you just write A, so this is a default. If you explicitly write this address, for example, this number 4 or number 3, so this means three continuous components of A4 to A6 and A3 to A5 are sent. Okay. So this is a definition of the starting address. Okay. So if you don't specify any address here, so this means starting address is A1 or A0. But if you explicitly defined, so it is like this. So this is a definition of the starting address of the sending buffer. And the receiving buffer is also same. Okay, so I just skip the details of the receive buffer here, but you can do in same way. Okay, so next I'll talk about some examples of MPI reduce. Okay, so this is a API, and if we have double operations of the x0 and x1, and this is a sending buffer, and this is a receiving buffer. So size is equal 1. Okay, and we have several processes, and each process sends x0. And among those, the MPI reduce picks up the maximum number. Okay, so that one is going to x1. Okay, and that is stored number 0 rank. So this is a operation of the MPI reduce. So this is a very typical case. Each process has x0, and the largest one among those is x1, and that is stored in number 0 process. So next one is very similar, but we have arrays with a size of 4, yeah, and x0 and xmax. And you can see, so x0 and xmax, and so this is a count. Okay, so remaining part is same as this one. So this means we compare the inch component of x0 from 0 to 3, and the largest one is going to corresponding address of xmax in the number 0 rank. Okay, so yeah, that's it. So explained here. So this is how we do this in the array operation. Okay. So does it make sense? Okay, so this is very will be very familiar with you. So this is exactly same operation for the dot product. Okay, so x0 is a local values, and this x sum is a global sum, and we are calling MPI sum. And so, for example, if you think about the dot product, and the local result is x0, and the global sum is x sum, and it's stored in number 0. Okay. So this is a dot product case. Another interesting case is so we have a x0, so length is equal to 4. And here we are doing the MPI sum for two components. This is the starting address of the sending buffer, and this is the starting address of the receiving buffer. Okay, and in this case, global sum of the x00 is going to x02. Okay, and the global sum of x01 goes to x03. Okay, on the number 0 process. Okay, so because so we are using a different address for the sending buffer and receiving buffer. Also, the name of the array is the same. So this is allowed. But if it is x00, it is not allowed, okay? Because we are using the same address for the sending and receiving buffer. Okay, so as the first part of this MPI reduce, I showed the address of the sending buffer and receiving buffer must be different. So that means this type of the computation. Okay. Any questions so far? Okay. Okay. So we have now we can calculate the dot product by MPI reduce. But the problem is it just stays on the root rank, a single rank. And if you calculate the conjugate gradient, all processes must have the same result for the dot product. And in order to do that, so we have another function. It's a broadcast. And the idea is very simple. And broadcasts a message from the process with a rank root to all other processes of the communicator. It's a name is a bcast, but what it is doing is a broadcasting. Okay? So in this case, we only have the buffer. So it's a sending buffer. Okay? And it's also the starting address of the buffer. And count is the size and the data type and root rank and the communicator. Okay. But so we have a very convenient function which combines broadcast and reduce. So it is a all reduce. Okay, so you can see it's a MPI reduce plus MPI bcast. And in this case, if you do some reduce computations by MPI reduce, and so all the results are copied to all processes. Okay, so that you don't have to call MPI reduce and bcast. So if you call MPI all reduce once, it's okay. Basically, interface for the MPI all reduce and reduce are same. But so you can see in the case of the MPI all reduce, we have no root. Okay, so therefore we have fewer arguments by one. Okay, sending buffer, receiving buffer, so message size, data type, and the operations and the communicator. Okay. Okay, so we have several operations for MPI reduce, and so generally, so we are using MPI max or minimum, sum or product or logical AND. So we have many other functions, but probably they are mostly most frequently used one. Okay. Anyway, so this is a very convenient functions. Okay. Any questions so far? Okay, so let's utilize this function to the dot product of this vec and vec. Okay. So before going to the computations, we need to construct the local data. And yeah, we have already discussed about that yesterday. But so length is 20, and so we have 4 processes. So that means each process handles a vector with length equal 5 in order to get the well-balanced computing. Okay, and so generally, continuous components are going to each process like this way. Okay, and for example, so number 2 process, so 10th to 14th will be go there. But at the local part. Okay, so the numbering will be start from 0. So this is very convenient rather than using the global ID. Okay, because we are running the same processes for all for this segment. So in that case, so program should be identical. From that point of view, these numbering should be starting from 0 or 1. Okay? So this is very natural way. Okay? Yeah, basically, so this is a very important point and starting point for the renumbering. And I already mentioned about so numbering of the external node yesterday. So in that case, it's more complicated. So this is corresponding to the numbering, local numbering of the internal node. Okay, and so this is very simple, but so this is very so fundamental and important. Okay, so anyway, so this is the original global numbering, and so this is a so local numbering. Okay. Okay, so let's go to the this all reduce dot c or all reduce dot f. Okay. So in this case, we are handling the only 5 components for each process. Therefore, size of the BEC-P and BEC-S is 5. Okay. And we are calling MPI init, MPI com size, and MPI congrang. And we have two kinds of sum, okay, sum A and sum R. And in this case, n is equal 5. And so we just so introduce each component of BEC-P and BEC-S as 2 and 3. Okay. And you can see, so sum 0, it's a local sum, is equal to the so sum of the so each component of BEC-P by BEC-S. So here n is 5. So we are doing so this 5 loop computations for each process. And we have 4 processes, and totally, so we have a length of 20 loops. Okay. So this is a local sum. Okay, so next we are calling some MPI functions. First, we call MPI reduce. Okay. And sending buffer is sum 0, receiving buffer is sum R. Okay. And the size is 1. It's a double precisions. We are doing MPI sum, and it's going to the root process, number 0, and MPI convert. Okay. So next, we are calling the so sum 0, MPI all reduce here. Okay, sorry. And so target is sum A. And so this is a so message size, and the MPI double, and MPI sum. So in the case of this MPI all reduce, so we have no information about root. Okay, so this means all the result are so shared with the sum A. So next, we write the sum A and sum R for the each process. Okay, and you can see it's a before bcast. So at this stage, so result is 120, and sum A is 120 for all processes. But you can see sum R is so 120 at the number 0 process. But other part, it's still 0. Okay? So yeah, you can expect that type of result here. And after that, sum R is broadcasted from process 0 to other part. Then after bcast, so we write the sum A and sum R from each process. So at this stage, all the values of sum A and sum R on all processes are equal to 120. Okay, so it's finished. Okay, so I just explained that. Okay, and so yes, so we have three functions: reduce, all reduce, and bcast. So actually, so all reduce is a reduce plus bcast, and so they are doing the same operations finally. Okay, so let's do this computations. So you can find so this type of result. Okay, and please go to the Odyssey and log in and going to the MPI S1. And please type module load fj and return. So this is the Fortran case, and this is the C case. And please modify the go4.sh and so submit so, go4.sh. Then you can get this type of result. Okay. Okay, so please do this now. Okay, so I can show you some demo. Oops. Okay, please go to the S1 and MPI module and so MPI FCCPX N クランなんだっけ KFAST か KFAST all reduce.c. So then you can get a dot out. And you can modify this go4.sh. Okay, so it should be lecture 7.0 and so GT17. Okay, so please check this group name and resource group. Okay, and the PJ sub go4.sh. Okay, and it's start running. Okay, it's finished. Okay, so this is the result. So actually, the format is a little bit different, but you can see, so before, after for process 2, 0, 1, 3. Okay, and this one is this column is sum A, and this column is sum R. And you can see, so sum R is 0 before B casting, except the number 0 process. Okay. Okay, so please make sure so you can get so this result. Okay. So any problems for compiling or submitting the jobs? Okay. Okay, so any problems or questions? Not just.
Yes, thanks. Yes. But I can find the resources file.
Okay, so you need to copy the file. So please go to the so very not this one. So MPI not this one. MPI Pro yeah 1F. Go ahead. Okay. Just this page. So please copy. Before that, please copy. Yeah, this one. Yeah, probably this one. Yes.
Okay.
Okay. So any other problems? Oh, okay. So you have some questions.
Try to run this comment, but the error is catastrophic error. Perhaps
So did you copy and paste?
Yeah.
Yeah, you should type because it says some multi-byte.
It's fine, right? It's this file.
Yeah, this file.
But when I try to compile it,
Yeah, but it says some multi-byte characters are included in this command. So probably you should type by yourself.
okay.
Yeah, please don't copy and paste from the PDF file because sometimes it includes multi-byte characters and they are not accepted from the Linux. Yeah, because my file is developed in the Japanese OS and yeah, basically it's English, but they may have some problems.
Yeah.
Okay. Okay, so I will wait 2 or 3 minutes more. Okay. So any other questions or problems? And also, you may know the very convenient tips. So if you push the page up, so you can go back to the previous commands like this. So especially, you are doing this type of the very complicated operations. So you can just change the name of the file, okay? Like this way. So you don't have to type everything every time. Okay, so any other questions or problems?
Try to run the sub go for the error is displaying on the page.
Just, when do you have this error? At the time of the
When I try to this comment.
can you edit? Can you open? Go for that sh. Yeah. So open. I mean Emacs or VI by editor. No. Go for the sh.
This one.
Yeah. Because so you need to edit.
Oh.
Go for the sh. Yeah. Do you use Emacs or VI?
Emacs.
Okay. So Emacs blank. Go for the sh.
This one. Like
Yes. And you need to change. So tutorial role should be lecture 7. No. This one. This resource group.
this one.
Yeah, lecture 7O.
Capital L.
No. So I showed yesterday, so you can go back. So go up, go up. This is go one. But you can go to the next page. No, next page. So next page. No. This one. Yeah. You just follow this.
Only this.
No, it's on GT17. GT00 should be GT17. Okay. And lecture 7. Oh. No, it's okay for the 4. Okay. Yeah, that's fine.
How to
Yeah, use it.
wait. Exit.
Oh. Yeah, you should run Emacs because you cannot do anything without that. Okay, it's submitted. PJ start. Hi, PJ start. Yeah, it's running. Okay. Okay, so as I mentioned in the first day and also in the call for participants, yeah, please master editor on the Unix, okay? Emacs or VI or yes, yeah, we have many new ones, and so yeah, if you don't use editor, you cannot even modify the shell script, okay? So because you need to change the shell script, so please master the editor, okay? And also please make sure this job script. So as I mentioned yesterday, so this resource group should be lecture 7O or lecture O after the class. Okay, and this group number must be GT17. And actually, so the shell script which you are having now used for other classes before. Okay, so these information might be different, and please check before running. Okay. Okay. Okay, so let's go to the next part. Okay, so next part is very, this is a very interesting part, scatter and gather. So this is some kind of combining the local operations and global operations. So this is a very simple process. So we have some vector and we just add one constant to each component. Okay. Yeah, what we are doing is parallelize this loop. Okay. And in this case, ng is equal to 32. It's a global size of the vector. It's very small. And alpha is 1,000. Okay. And the process of number of the MPI is equal to 4. Okay. So actually, you can find the original component of VecG in a1x.all. So it's starting on 101, 3, 5, 6, 9, 11, 21, 51. Then 200, 300, 400. Okay. And so yeah, it's very easy to recognize. Okay, so we have 8 components every 100 values. Yeah, actually, the calculation itself is very easy. So just add 1,000 to each component of these. Yeah, it's easy, and we don't need even computer. Okay, but so we try to do this on the parallel computer. Okay, so I just type this a1x.or. Okay, so I think you can find a1x.or here, and yeah, it's like this way. Okay. Okay. So this is a procedure. So reading vector vecg from a1x.or with length equals 32 from one process. So it's a number 0 process. So it's a global data. Okay. And distributing vector components to 4 MPI processes equally. And this means so length equal 8 for each process. Sorry. And this is a local data and a local ID and local numbering. And adding alpha to each component of the local vector, so with length equal 8 on each process. Okay. And merging the results to global vector with length equal 32. Okay, starting from the global data, and it's distributed to the local process, and doing a parallel processing for each local part. And finally, so the local process is merged. And actually, we don't need parallel computers for such a kind of the small computations. But so yeah, we can confirm the operation is so working properly in such small cases. Okay, so this is a Fortran, and this is a C. And okay, so NG equals 32 for both cases. And so VecG is a vector, and the size is equal to 32 and NG. And we call MPI init com size and com rank for both of the cases. And then, so if the my rank is equal to 0, so we open the a1x.or and here, and read the component. Okay? And you can see, so VecG is so read from this a1x.or. Okay, so distributing into the 4 processes is done by MPI scatter. Okay, so this is a very convenient function. Okay, so this sends data from one process to all other processes in a communicator. And S count size messages are sent to each process. Okay, so we have so 3 arguments for each of the sending part and receiving part. Okay, and the root and the communicator. Okay, so you are very familiar with the sending buffer and the receiving buffer. It's a starting address of the sending buffer and also the receiving buffer. And the S count is the number of elements sent to each process. And R count is number of elements received from the root process. Okay, and so send type and receive type. Okay. Yeah, actually, generally speaking, S count and R count are same, and send type and okay, and so we don't know why this kind of the duplicated information is defined, but probably at the early stage when the developers MPI thought so the function must be flexible. So that's why they provide a duplicated data set. But generally speaking, S count is equal to R count, and send type is equal to receive type. Okay. Okay. Okay, so as I mentioned, so usually S count is equal to R count, and send type is receive type. So please don't be confused. And this function sends S count components starting from send buff at process root to each process in communicator. And each process receives R count components starting from receive buffer. Okay, receiving buffer. So this is operations of this MPR scatter. Okay, so this is the interface of the MPR scatter. And this is how we utilize in our case. Okay. And you can see, so this vec is a local vector, and the size is equal to n. So n is equal to 8. And so this is a MPR scatter. So this is a sending buffer, and the size message size is n, so 8, and MPI double precisions. Okay. And this is a receiving buffer. It's a local vector, and size is n, and also the type is MPI double precisions. And the sending rank is number 0. So because vec G is read from the number 0. Okay, and the communicator. And in the case of the Fortran, we have error code. So this is the same for the C, and the vec G n MPI double, and the vec n MPI double 0. Okay. So you can see S count and R count, S type and R type are same. Okay. And so this is internal operations. Okay. So basically, MPR scatter is doing the processing the arrays for the same uniform length. Okay. So in this case, all the receiving buffer size is equal to 8. Okay. And the 8 components are scattered to each process from root 0. And so first 8 components of vec are stored as a process 0. Okay. And the 9th to 16th are also going to the this number 2 process. Actually, it's process 1. Okay, like this way. But local numbering is starting from 0 in the case of the C, and 1 in the case of the Fortran. Okay. So this is a very interesting and convenient function. Okay, so any questions for this part? Okay, so next part is doing the just writing the content of vec, okay, at each process. Okay, so this is the before doing the operations. And you can see, vec, local vector is all stored in the from 1 to n, or 0 to n, 0 to n minus 1. Okay. So this is based on the so-called local numbering. Okay. And this is a result. So before computations. So this is a process ID, and this is a local ID. Okay, and like this way. And the next part is doing the computation on each process, and from 1 to n, and vec 1 is equal to vec I plus alpha. Okay, for both of the C and Fortran case. And if you write this result after computations on each process, it's like this. Okay, So if you compare with the result in the previous page, just adding 1,000 for each component. And you can easily recognize whether the operations were done properly or not. Okay? Okay, the final process is so gathering the all local result to the process 0. Okay? So in that case, we use MPI gather. So this is the inverse operations to MPI scatter. Okay? So this is the interface of the MPI gather. And you can see, so this is the same interface. Send buff, S count, send type, receive buff, R count, receive type, and root and com. Okay? And in this case, receive buffer is on the root process, and send buffer is from each local process. And also in this case, S count is equal to R count, and send buff is send type is equal to receive type. Yeah, like this way. And so this is how we write. And in this case, sending buffer is a local one, and the receiving buffer is a global one. Okay, so you can see we are doing just reverse computations. So in this case, each of the process is sending the local vector whose length is equal to n. So they are equally distributed. Then, so these vectors are stored in BecG, so in the sequence of each process in this way, okay? Like this way. Yeah, processes are just so reverse of the MPI scatter. Okay, so yeah, let's try that. Okay. We have a code here, scattergather.c and scattergather.f. And so if you compile, and you can modify gopher.sh. And actually, so you can use the same gopher.sh for the dot product. Then run the code. Okay. We also have the combined functions, reduce scatter. But I have never used this, and I just show you for the reference. Okay. And also we have a convenient function all gather. So in the case of the gather, the result is just on the number 0 or one process. But in the case of the all gather, so all the results are shared by all processes. Okay, and so sometimes this is very convenient. And all to all is, as I mentioned, it's a transformation of the dense matrix. Yeah, it's very so widely used in FFT, but it's not the case in this class. Okay. Okay, so I think you can try this scatter gather.c. And yeah, please make sure this go for.sh. Okay. And lecture 7.0 and GT17. Okay. Okay, so it's running. Okay. So this is the result. And I think, I'm not sure it is writing the final result, but so you can see, so it's this one. Okay, so last one is So yeah, you can see we have a little bit so before is and after so there's a local result. And this final result is written in the root process, and they are writing the global mesh, okay, a global result. But you can see the sequence is a little bit confusing. And after this, so process 3 and process 1 results are written. Okay. Yeah, in the case of the MPI, so this kind of things sometimes happens. Okay, and so yeah, because all the processes are writing the result simultaneously, and so sometimes so this happens. But anyway, so this final means a final global result on the root process. Okay, so I think it's 10 past 7. Okay, so any questions for this part? Okay, so let's take a break now, and we start the class at 10:15. Okay. Okay, so next part is so operations on distributed local files. So in scatter gather examples, process 0 reads global data that is scattered to each processor. Then parallel operations are done. If the problem size is very large, a single processor may not read entire global data. So if the entire global data is decomposed to distributed local data sets, each process can read the local data. If global operations are needed to a certain set of vectors, MPI functions such as MPI gather, etc., are available. But so practically, yeah, we usually distributed the local data before the computation, like this way. Okay. So this one is just dividing the A1x.all into 4 parts. Okay. So you can see this is number 0, 1, 2, 3. So this file.c is just doing the reading these files. So in distributed manner. Okay. So I skipped running this one, but you can do this later. But I just describe the content of the program. Okay, so you can run this code using go4.sh. Okay, so please make sure to change this resource group and so group name. Okay, so this is a file.c, and so in this case, the size of the vector is equal to 8. And so we are doing the MPI init com size and com rank. And using this my rank ID, so we are creating the name of the file, local file. So A1 dot, so this my rank. Okay. Value is a read in this my rank. And open this file, and so just read each component of the big I. So in this case, we have 8 components and reading these files. And just writing on the screen. So that's it. And call MPI finalize. So you can see, so we are just reading the different file. Okay. And the next one is this is a very typical SPMD operations, you can see. So yeah, we are running the same code, but the data is different. Okay, so each process is reading different data. Okay. And the next one is a non-uniform vector length. Okay, they are reading A2.0 to A2.3. Okay, and so name of the program is file2.c or file2.f. So this is a file, and you can see, so they have a variable length of the data. And the first line shows the size of the vector. Okay, so in this case, this is 8, 5, 7, and 3. And so this is a program, and this is very similar to the file.c or file.f. But in this case, so size of the vector is variable. Okay, and so you can see. So here first we just open the A2.0 to A2.3, and first we read the number. Okay? Number is the length of the vector. And we allocate the vector where the length is equal to num. And we read each component of the vector and just write down. So this is also the very typical SPMD operations. So in this case, of course, A2.0 to A2.3 are different files. And also this num, okay, length of each vector. So, okay. So this is also different. Okay? And so it's a very typical SPMD operation. So how to get the general, how to generate the local data? One is reading the global data, n equal ng, and scattering to each process using MPR scatter, and parallel processing on each process, and if needed, reconstruction of global data by gathering local data. And generating local data, n equal n, or reading distributed local data is another way. And generating or reading local data on each process, and parallel processing on each process. And the reconstruction of the global data by gathering local data if you need that. So basically, in the parallel finite element case, so the second approach is dominant, and yeah, probably tomorrow and Friday, so you are mainly working on this part. But so today and tomorrow, or today and tomorrow morning, so we are using both. Okay. Okay. So any questions about this part? Reading distributed files. Yeah, this part is very easy. Okay. And so let's go to the last part. So MPI all gather V. And this is a more flexible computing. So in the previous part, so you use the MPI gather and MPI scatter. But so we have some restriction. So length of message from to each process is uniform. Okay. In that case, it was 8. Okay. But MPI gather V or scatter V extends functionality of MPI scatter and gather by allowing a varying count of data from each process. So MPI gather V, scatter V, all gather V, and all to all V. And I'll show you some examples, and the exercise is utilizing these functions. So this is the interface for the all gather V. Okay. Basically, MPI gather V and all gather V are same, and so I just show you the all gather V. And the variable count version of MPI all gather, and create local data from create global data, from local data. Okay, so we have several arguments: send buff, S count, send type. And the receive buff, But you can see R count is a R count this time, and disputes and receive type. And you can see, so we have two additional or different arrays for this type of the variable computations. So basically, so send buff, S count, send type, receive buff, and receive type are same. And some features are so R counts and disputes. Okay. So I think I have more details. Yeah. So this is a definition of the R counts and disputes. So R count is a so integer array of length of the group size, containing the number of elements that are to be received from each process. So array size is a p dot. P dot is a number of processes. Okay, and the disputes is also the integer array, and so entry I specifies the displacement relative to receive buff, at which to place the incoming data from process I. So size is p dot plus I. So actually it's from 0 to so process number. So these two arrays are related to the size of the final global data. Therefore, each process requires information of these arrays. So R counts and disputes must be shared by all processes. Of course, the content must be same. Okay, and usually, actually, so we don't need this because this is introduced very flexible way of the computations. So yeah, if you explain more briefly, okay, so R counts means the number of elements which are sent to each local process. Okay, so this is a message size from each part. And the disputes so this is a long receiving buffer. And the disputes is a starting point of the array for each process. Okay. So because so this computation allows this type of some gap, okay, between the ending part of this process 0 and the starting point of the process 1. And we call this difference between disputes 1 to disputes 0 for the stride. Stride doesn't explicitly appear in the program here, but yeah, we can say that. And the sum of the stride is equal to the length of the receiving buffer. Yeah, this is the idea. Okay, so each process is sending n. Okay, so n is different, but locally it's n. Okay, so it's a SPMD. Okay, and so they are sending the global data here. Okay, and so this n is corresponding to the R counts. Okay, and so yeah, stride is some buffer for each process. But so usually we don't need this type of merging. Okay. Therefore, so in this class, or in this case, we just think about this case. So in this case, stride is equal to R count. Okay, and we have no gap. So this means so if you have a data of the R count, so you can easily create the information of the disputes. So because R count is just accumulation of the disputes is just accumulation of the R counts, and you can easily create the information of the disputes. Okay, so this is how the NPI altogether V is done. Any questions? Mm. So could you repeat? Mhm. Yeah, because yeah, it's better to see this. You can see, so R count is so 0, 1, 2, 3. And you can see this is this one, this one, this one, this one, and this one. And the last one is this is 4. Okay?
So it comes to the end of the
Hmm. Hmm. Okay, any other questions? Okay. Okay, so I'll show you some more detailed information. And the R count is the size of the message from each process, and the size of the local data, and the length of the local vectors. And the dispute is the address and index of each local data in the vector of global data. And the dispute p dot plus 1 is the size of the entire global data. So it's a global vector. Okay, you can see so this one. So this is how we prepare for utilizing the MPI altogether way, because we need to prepare disputes and R count before using MPI altogether way. And as I mentioned, so each process needs information of R counts and disputes. And R counts can be created by gathering local vector length n from each process. On each process, disputes can be generated from R counts on each process. Because in this case, stride is equal to R counts. And the size of receive buff is calculated by sum of R counts. Okay, so that's what we can do now. Okay, so next part, you can see the agv.c. So this function is preparation for MPI altogether V. Okay, so what they are doing is so final purpose is generating global vector from A2.0 to A2.3. So as I mentioned in the file 2.c and file 2.f. So it's a variable length file. And the length of each vector is 853, 857, and 3, respectively. Therefore, size of the final global vector is 23. So you can easily count 13, 20, 23. Okay, so this is the content of the A2.0 to A2.3. Okay, so I'll show you the content of the MPI, agv.c. So it's a preparation for MPI altogether V. Okay, so you can see, so R counts and disputes arrays. And first we call the MPI init, com rank, and com size. And reading the A2.0 to A2.3. Okay. And so we are allocating the vector according to this first line, this n. Okay. Then we read each component of vec at each process. So far, it's same as the file 2.c or file 2.f. Okay. So next one is so we allocate the R counts and disputes. Okay. And the size of the R count is p dot, and the disputes of the so size is the p dot plus 1. So where the p dot is this one, okay? MPI com size. total number of processes, sorry. Okay, so at this point, we write the content of R counts, but that should be 0, okay? So next thing we are doing is so calling MPI all gather, okay? So in this case, sending buffer is n, send count, S count is 1, because we are just sending the one component. And the type is MPI int. And the R count is so receiving buffer. And also the count is 1. And so type is MPI int and MPI convert. So this means so all the processes have the same R count, okay? Who has 4 components. And each component is corresponding to n for each process, okay? 8, 5, 7, 3, okay? Like this way. So you can confirm that, so after this, by writing the content of the R count. Okay, so does it make sense? I think I have a, okay. And also this means all the processes share this R count. And the next thing is we just create a dispute. So this process is done in parallel manner on each process, so separately, okay? First of all, dispute 0 is equal to 0. And yeah, actually, so dispute is just accumulation of the R counts. And we are just doing, so accumulate the value of the R count to dispute 1 in this way. Then we can easily create the dispute. Okay. And finally, so you can write the content of the dispute here. And so actually, so this is the end of this program. Okay, so if you go to this directory and compile the agv.c and run the code, and you can get this type of the result before after dispute. Okay, so this first column is showing the process ID, and so I think next one is writing the n on each process 8537. Okay. And so we have 4, 0. So these are the initial value of the R counts. So before computations, okay? Before calling MPI altogether V. And after calling MPI altogether V, so all of them has 8573, 8573. And the third line, dispute is my rank and the content of the dispute. Okay, it's starting from 0 and 8, 13, 20, 23. And you can see all the processes have the same content of the disputes. Yeah, because they are sharing the same value of the R counts, and so they are doing the same operations on each process. Yeah, so that's obvious. So we have a same value on disputes. Okay, so this agv.c is a preparation for the MPI altogether V. And actually, receive buff is not defined yet. And the size of the receive buff is equal to the dispute p dot. And finally, what we have to do is, yeah, like this way. Vec is a local vector. So n is a local size of the vector, and MPI double. And the receive buffer, and R counts and disputes are already created, and MPI double, and MPI convert. Okay, so if you add so this type of several lines, so you can complete the operations of the MPI altogether V. Okay, so I think we have time, and yeah, let's try to calculate AGV.C, okay, by yourself, and so see what is happening. Oops. Okay, so this is a AGV.C. And yeah, you can use the same go4.sh. Okay, and if you open the test.list, it's a little bit complicated. Yeah, like this. Okay, so you can see, so this is number 3, number 0, and number 1, and number 2. And so before and after shows, so the second one shows n, okay, size of the local vector. And the continuing for part is showing the contents of the R count. Okay, so 8573. 8 is from this number 0, and the 5 is number 1, and 7 is from here, and 3 is this number 3. Okay, so you can see all of the processes share the same value. And the next one is a disperse, and so it's starting from 0, and 8, and 13, and 20, and 23. So it's accumulated. And so disperse are also shared by all processes, so same values. Okay. Okay, so please check this. Okay. Okay. Any questions for this part? Actually, so extending this, so completing this MPI altogether V is one of the target of the exercise in the next slot. And yeah, so you need to read the code carefully. And if you have any further questions, you can ask in the next slot. So any questions? Okay. Okay, so this says report, but this is just a exercise. Okay. And we have 3 problems. So one is read the local files A1.0 to A1.3. It's a uniform length, and A2.3 to A2.0 to A2.3. So they are variable lengths. And develop the code which calculates norm L2 norm of global vector for each case. Okay? And basically, so you can just modify the file.c or file.f and file2.c and file2.f. So reading part is already available, and what you have to do is adding some MPI reduce or MPI all reduce part. So next part is a developer code which constructs the global vector using MPI altogether. So yeah, this is just a corresponding the extending the AGV.C or AGV.F to the this operation. So we have a third problem. It's a little bit so more advanced one, and develop the parallel program which calculates the following numerical integration using trapezoidal rule by MPI reduce, MPI bcast, etc. And the measure the computation time and the parallel performance. Okay? So this is a target integration. Okay? And actually, 1 over 1 plus x squared from 0 to 1 is equal to pi over 4. So therefore, the result of this integration is equal to pi. Okay, and actually, you need a 5 or 6 trapezoidal to get the accurate solution. But in this case, the target is measuring the parallel performance. So you need to apply the 100 millions or billions of trapezoidal. Okay, so report is not so needed here, but so you can just do these three problems in the next slot. So this is how you change the number of processes, and I believe you can find these sample shell script in the directory. Okay, so finally you can use up to 576 cores. Okay, so in that case, node number is equal to 12, and MPI proc number is equal to 576. Okay, yeah, like this way. Okay, so this is a exercise, and yeah, you can try this. Oh, sorry, this is a calendar. Okay, so now it's almost it's still 10:46, and you can start the exercise now. And I believe so remain of this slot, and the next slot until lunch break will be exercise. Okay, and I have no lecture, and you just try to do the programming for this part. Okay, and from 10:10, I start to explain the sample program for this exercise. Okay? Yeah, you have only very small power, but I hope at least the first two problems could be done in 1 hour. Okay. So if you have a time, so you can try the last one for the numerical integration. Okay. So any general questions so far? Okay, so let's start the exercise. And also you can discuss with your colleagues. So it's okay. So because it's not a grading, and so it's no problems. And if you have any questions, so you can talk to me. And and if you want to have a break, so you can take if you like. So basically, so until lunch break, so yeah, you can use the time by yourself. Okay, so let's start. So good afternoon. And so how was the exercise? Some of you made it. Okay. Yeah. So I'm sorry. So the time is not so enough, and so even if you tried, probably it's hard to complete everything. But anyway, so I'd like to show you that how to do this. So if you go to the home page, so you can find the report S1 for Fortran and C, and I believe you can download some files here, and yeah, it's already uploaded. Okay, so yeah, I'll explain this material. Okay. Okay, so this is just repeating the problem. So we have 3 problems, and so the first one has some 2 sub problems. Okay. Okay, so if you log in to the Odyssey, and so you can copy the sample file. So this is a Fortran S1RF dot and S1RC dot, and you can copy to your directory. And so please don't forget this blank dot. Okay. And if you so go to this top directory, and so open this file, and so you can find the S1 ref underneath this MPI directory. Okay. Okay, so let's start the first one. Okay, this one is not so difficult, and so we have 2 types of the distributed files, and read these distributed files, and so develop the code which calculate norm. So L2 norm. Oops, it's going. Okay, so yes, I'm sorry. So it's some network problem. I don't know what is happening, but it's too slow. Okay, okay, very sorry. And please copy your file, and you can find these so directory. Okay. So basically, the first problem is not so difficult, and please use the NPI all reduce. And the advice is checking each component of the variables and arrays. Okay. Okay. So again, so this is a okay. And so I just skip the details. So here, and so yeah, I just repeat something which I mentioned this morning. So one is so sending buffer and receiving buffer, and we have some so operations. And this time, so we are so just using this yeah, only one values, and just calculating the MPI sum. Okay, so this is the MPI bcast, and yeah, basically, so we can use so MPI all reduce.
Is
Some problem. But now it's okay. Now it's okay. But I don't know why it. Okay. Okay. So MPI all reduce is a combination of MPI bcast and MPI reduce. So generally speaking, so I recommend you to use this. Okay. So because it's very convenient for parallel finite element case. Okay. So in this case, you don't need any information about the root. Okay, so this is the first one. So you can find so S11 for A1.C. Okay, so this is a very long name. Okay, and actually, so we have 2 codes for the S11. Okay, one is for A1 and another one is for A2, where the vector lengths are variable. Okay. Okay, so I think it's a very small. It's just a one page. Okay. And you can see, so we start from the MPI init, com size, and com rank. And we are reading so the file A1.0 to 3. Okay? And I think up to here, it's same as the so S1 file.c. Okay? After that, sum 0 equals 0.0. And this is a so local sum. Okay? And so sum of the square this vector, okay, is so accumulated to this sum 0. Okay? And the next one is so MPI all reduce, and sum 0 is accumulated to this sum because we are applying this MPI sum. Okay? And message size is 1, it's a double operations, and the MPI sum and the MPI convert. Local value, so it's different for each process. But this value sum is so same value for all processes. Yeah, because the local sum 0 were accumulated to this sum. So basically, so we are applying the MPI all reduce. Therefore, all processes share the same value. And the sum, so we take the square root because it's a so sum of the square. And in order to calculate the norm is the length of the vector. We need to take the square root. So this is a so result. Okay, and we can write result here. And in this case, so we just write from the rank 0. Okay, so this is the first one. And the second one is also so easy. And so we just read the A2 dot something. And the first line shows the so length of the vector. And we allocate vector according to this n. And we just read each component of vector. And after that, it's same. Okay? And we just calculate the local sum 0, and apply the MPI all views. And sum is equal to square root sum. That's so this varies. Okay. Okay. So any questions? And you can run the code, and so you can get some result. And in the directory, so you can find .a1.f and .a2.f. So this is a so Fortran program, so calculating this result. So in the serial code. And actually, so you can run on the so login node, but I recommend you to run using batch queue. Okay, and please compile by frtpx, and so yeah, you just submit this go1.sh, and you can get the so result. So A1 dot something is this one, and another one is this one. And so these are the result by the so parallel computer. Okay, and you can confirm that parallel computing provides a accurate solution. Accurate is not good word, so proper solution. Okay. Okay, and so basically, as I mentioned, so address of the receiving buffer and sending buffer should be different. Okay? So I've never done this, but if you try the same name of the so scalar, it provides some errors. Yeah, it depends on the so systems or compiler, but so generally, so it doesn't work. Okay, so please apply the different name. Okay, okay, so this is a so overview of the so first problem, and also if you have an array here, so as long as you are using a different address, so this is okay. Okay, so any questions for this part? Okay, so I just learned how to do this on the, so, okay. Yeah, you can try by yourself later, but I just show you some. GT00。Okay, oops. Yeah, network is so slow. And you can go to this S1 ref. Load FJ. And so S1 or A1.C. Okay, and so modify the go.sh. Okay, so it should be GT17. Okay, CSR. And also you can find one.fa. So for example, you can actually, so you can run on the login directory on this. Okay, and so this is the result. Okay, if you use a G-Fortran, you can run this code on the login node. Okay, so this is a so one CPU code, and you can see the results are exactly same. Okay, and the parallel computing provides a so proper answer. Okay. Okay, so any questions for this part? Okay, so next, MPI altogether V. Okay. And you have already prepared the so MAGV.c, and what we are doing is so just merging so these so local vectors with a different length, and so so combine these and get the global vector. And just see. Okay, so this is an overview of the MPI altogether V, and so Okay. And so you can see send buffer, S count, send type, and receive buffer, R count, disperse, and receive type, and communicator. Okay. So this is a more okay detailed description of the R count and the disperse. And here, so this is a general case, and we allow this type of the margins. But in this class, we just apply this type here, this type of approach, and you can see. So in this case, stride it is okay, and so R count means so size of the message for each process, and display is the address and index for each local data. Okay, and so this is the procedures, and the R counts can be created by gathering local vector n from each process, and on each process, displays can be generated from R counts on each process. Okay, so in this case, stride I is equal to R counts I. And the size of the receive buffer is calculated by summation of R counts. Okay, so the AGV.C, so which I just described in the last part of this morning, it's generating, so it's a preparation for the MPI altogether V. So length of the vectors are 8, 5, 7, and 3. And yeah, we just prepare for the MPI altogether V. So this is a vector. And so you can see at the first line, it provides a length of the vector. Okay. Okay. So what we are doing, so read local vectors, create arrow counts and disputes, and prepare receive buffer, and do all together. Okay. So actually, so we have already done up to this. And so we have very few things to do. Okay, so next page shows a S12.f, S12.c. And so actually, so beginning part, so agv.c. Okay. So first, we are calling MPI init, com size, rank, and open the A2.0 to 3, and reading the so n and each component of the vector. And we allocate the R counts and the disputes, and the size is p dot and p dot plus 1. And so using the API altogether, so we create the R counts. Okay. And as I mentioned in this morning, so R counts and disputes must be shared by all processes. Okay. And each component of the R count is n, and n is so length of the vector for each process, and the size is 1. Okay. 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 So MPI altogether is the MPI gather plus MPI pcast. And all so result of this so receive buffer is shared by all processes. Okay, so I think we should. So could you wait one while? And I think we should exit from the this environment. Okay, so very sorry for interrupting. So I just restart. Yeah, this part is the same as before, and so you can see. So this put is calculated by accumulated by the R count like this way. And so up to this part, so you have already done in the agv.c in this morning. And the next thing is allocating the global vector, and the size is a disparate p dot. Okay, because so this end address is the length of the so global vector. And finally, so you just called MPI altogether V, and the V is a local vector size, and it's a MPI W. And this is a receiving buffer. Okay, so this one. And this is a R count and this plus, and the MPI double. So this is the same type with this one, and the MPI convert. Then so you can create the so vector. Okay, you can connect the local vector to the global vector where the length is 23. And you can write this vector here. Then you can get the result. Okay, so can you see? So you just add these two lines to the original code. So that's it. So very easy. Okay, so I think I can do some demo with that. And you can try that later if you like. Okay. Okay. Yeah, I think it's much better than before. So thank you very much. Volume? Okay. How about this? Okay. Yeah, thank you. Yeah, it's okay. No problem. Okay, module load FJ and MPI S12.c and the PJ sub go4.sh. Okay. Okay, it takes a long time. Okay, it's finished. And this is the output. And so in this case, so they are writing before and after. So this is a this number shows a so process ID, and the second one shows the length of the vector, and so these are the so content of the R count, and they are writing the so resulting so final vector, okay, because it's shared by all processes, and they are writing the same information. starting from 101 to 405. Okay. Okay, so you can make sure, so afterwards. Yeah, because the vector components are very small number, just 23, so you can check, so by your, so eye. Okay, so any question about this part? Yeah, this is a result. Okay. Okay, so let's move to the third problem. So this one is a very new, and so I haven't talked about this before. But so you can, so if you remember the trapezoidal rule, so it's not so difficult. Okay, so actually, so this is a rectangular, not a trapezoid, but so basically, so this is a trapezoid rule, and you can divide the whole area into the very small chunks, and just add these. Okay. So in this case, you need only 5 or 6 trapezoid to get accurate enough solution. But in this case, our motivation is measuring the parallel performance, and so you can put a very small sizes of these rectangulars. So if you follow this formula, this type of computation is feasible. But so if you think about adding these values one by one, so this kind of approach is also possible. So in this case, for example, if we have 4 processes, we divide the whole area into 4 parts, okay? And so calculating each area. But in the case of the type B, so you can see the color is distributed in cyclic manner. So actually, is much easier, okay, for this one. Okay, I will show you the implementation of these 2 programs. Okay, so let's start for the type A, and so this is the S13A.C. Okay, and we have a separate file input that, and there we just read the number of segment. Okay, and so this is a very large one. And we call MPI init, MPI com size, and MPI com rank. And we also allocate the index. So index shows so it's a very similar to that of the CRS format. And so size is p dot plus 1. And so this provides a number of meshes or ID of meshes on each process. Okay. And the dx is a size of each mesh, and it's a 1 divided by n. Okay. And also we just apply the index I, and so index I is equal to I multiplied by n divided by p dot. Okay. Because the I could be very large, and we just apply the long type. Okay. Okay. And this is the procedures, and we are calculating each trapezoid mesh in this way. And you can see the starting point is index my rank, and so ending point is ending index my rank plus 1. Okay. And each part x0 and x1 is calculated for these 2 points. And f0 and f1 is a value at this point. Okay, so it's 4 divided by 1 plus x squared. Okay, and so the area is f0 plus f1, multiply by dx, and so divided by 2. So we add this value to the sum 0. Okay. And basically, so we just repeat for this process. And after that, we call MPI reduce. This time we are calling MPI reduce. And the sum 0 is a local value, and the sum is a global value. And just one size and double operations. And so we are taking the MPI sum. And the value is on the number 0 rank and calling MPI convert. Okay, so we are just writing the result if my rank is equal to 0, sum, and this value. So this value is an analytical solution. Okay, and also time is so this is the starting part, and this is the ending part, and time E minus time S is the actual computation time, including this communication. And these are recorded. So any questions for this part? Okay, so next part is type B, using this type of implementation. So this one is much easier to implement. So in this case, we don't need index array. Okay, so the loop is very simple, and you can see. So starting point is my rank, and the ending point is n, and so this cycle is p dot. Okay, so like this way. So every in this case, every 4 cycle, so you can get the same color. Okay, so thus you can get the same result. Yeah, this one is much easier. And you can compare the two types of the implementation. So one is a S1 3A dot F or C, and another one is a S1 3B dot F and C. And you can see by putting this minus small o, so you can specify the name of the executable file. So far, we didn't do this, and the default name of the executable file was a.out. But so in this case, so you can specify the name of the code, because we have several kinds of the code. And we have several shell script, and you can run many types of the cases. Okay. For example, so this A384.sh is using 8 nodes and 384 cores. Okay, and so because we have 48 cores for each node, and we use the full cores of the 8 nodes. Okay, and we are running the 4 types of the configurations. So one is type A or type B, and also another is putting this options. So this NUMA CTL minus L is utilizing the local memory as much as possible. But basically there are no effects. Okay, but you can just try. Okay. Okay, so if you change the number of the cores, you can just change the number of node and the MPI process. So this is a maximum case. Okay, so in this case, you can use 12 nodes and 576 cores. Okay. Okay, so this is the same figures which I showed yesterday. Okay, so I will show you the performance on Odyssey about this problem. So actually, so you can try similar things by yourself. Okay. And based on the result using a single core. And we ran 5 times. And that took the best case for the 5 runs. And if you compare the type A and type B, and type A is better, especially for the small cases. And so I cannot understand the reason, but so type B is very slow for the C language. And you can try that. So this is a strong scaling, and the entire problem size is fixed. And if you apply the n times cores, you may have the 1/n computation time. Okay, so weak scaling the problem size per core is fixed, but we don't do this for this case. Okay, so this is a result, and so this one is n is equal to 20 millions. Okay, and this one is so n is equal so 2 billions. Okay, 100 times. And you can see, so we are comparing case A and case B and ideal case. And this is a speed up. Okay. And you can see in the case of the case A and case B, so if the symbol is close to this line, performance is better. But you can see in the case of the case B, so the performance is saturated over so roughly 200 cores, okay, like this. In the case of the case A, it's generally good, but if you go to the very many cores, so it's a little bit smaller than the ideal case. In the case of the very large problems, okay, large problems, so both of them are very nice scalability, and so it's almost so ideal speed up. Okay, so you can see, so if you compare these 2 figures, if you increase the problem size, the performance is better. Okay. So this is a parallel performance. Okay, so 100% means so it's exactly on this line. If the problem size is small, this parallel performance is so going down, and especially so yeah, this case B is very significant, and at this so maximum case, the performance is less than 20%. So even for this case, it's so almost so less than 70%. Actually, so we are writing this line using this log scale, and it's decreasing. It's not so significant from this graph. But if you show the actual value, it's very significant going down. Yeah, you may know, so this type of the log scale graph is very tricky, okay? So if you have some very bad performance, so log scale is very good to hide that bad performance, okay? But anyway, so this one is very nice. And if you compare the values, it's almost 100%. And you can see in the case of the case B, we have a little bit so decreasing of the performance in the so 576 cores case. Okay, so this is a definition of the parallel performance. If you have one process and the computation time is 100, and if you have so 100 processors and the computation time is 1 second. So in that case, parallel performance is 100%. Okay, but so if you take the 100 processors and it took 1.5 seconds, so larger than this one. So in that case, the parallel performance is so 67%. Okay, so 1 divided by 1.5 multiplied by 100 is this 67%. So this is how we calculate the parallel performance. So generally speaking, so performance is lower than the ideal one. And this is a time for the MPI communications. So time for the sending data. And so this is based on the communication bandwidth. So it's a network speed between nodes. And the time is proportional to size of sending and receiving buffers. So another reason is time for starting MPI. So it's called latency. So it does not depend on the size of buffers. So every time you call MPI, so we have some overhead. Okay. So and also depends on the number of calling and increases according to the process numbers. So it's order of the roughly 10 microseconds. So synchronization of the MPI is also very similar to this one, and so increases according to number of processes. So in this case, message size is very small. We are just sending and receiving one scalar, okay, just 8 bits. Therefore, this overhead by communication by MPI is very small. So generally, they are from this so-called latency. Okay, so this is a very typical case. And so if computation time is relatively small, and in this case, n is small in S13, so these effects are not negligible. So I mean the overhead by communication. So if the size of the message is small, effect of latency is significant. And so granularity is a very well-known word. So it's a problem size per process, okay? And it's some criteria to evaluate the parallel performance, okay? For example, you have this kind of ratio for the computation and the communication overhead. So generally speaking, communication overhead depend on the frequency of the calling MPI. So that means communication overhead is not so big changes as long as you are using the same number of nodes. Okay, so that means if you solve the larger problems, so you have a smaller ratio of the communication overhead. Okay, but if you increase the number of nodes, computation time for each process is reduced. But generally speaking, this communication overhead itself is larger if you increase the number of the nodes, because we have a synchronization overhead by MPI. And you can see, ratio of the communication overhead is more significant in the case of the large number of nodes. So this is how we understand the parallel performance, especially in the strong scaling in this type of the program. Okay. I think this is the same. Okay. Okay, so this is the end of the number one exercise. And the last problem is very important. And yeah, I would like you to do the evaluation of the parallel performance by yourself. Okay. Okay, so any questions for this part? Okay, now it's 2 o'clock, 10 minutes. And so we take a break here. And after that, so I would like you to do some exercise. Okay, so you can develop your own code, or you can run the code which I provided. Okay, And let's start the next lecture at 10, 2:40, 30 minutes from now. Okay. And you can take a break now. And if you have any questions, so you can talk to me. Okay. Yeah, I'm very sorry for taking time for the network problem. Let's start next part. Okay, so any questions so far? Okay, so let's go to the next part. So next part is part 2. So it's about the point-to-point communication. Okay. So we start with the definition of the point-to-point communication. And actually, we have two small exercises so inside this. And so based on the 2D problem, so generalized communication table. So this is the most important part of this 5-day class. Okay. Then I'll talk about some exercise. Okay. Okay, let's start from this 1D case, and we have 12 nodes and 11 elements. Okay, and 3 domains. So this is how we define the each part, and this is a local data structure including external nodes. Okay, and this is a actual local data set. So you can see these internal nodes are starting from 0. Then we number the external nodes. Okay. So as for the element, so we have no specific method for the numbering the element. But in this case, we start from the elements just formed by the internal nodes. Then we go to the overlapped elements. And we have external nodes and boundary nodes. And the boundary nodes are part of the internal node, but that is a external node for other part, okay, like this. And we have the point-to-point communication between external nodes and boundary nodes, okay. So this type of the communication is called point-to-point communications. And this kind of the communication is just with the neighbors. And you can see, so we have no direct communication between number 0 and number 2. Okay. So this is a precondition conjugate gradient method. And here we are applying the diagonal scaling or point-to-Jacobi preconditional method, where this is our preconditional matrix. So we just extract the diagonal components of the original quotient matrix A. As I mentioned yesterday or this morning, and if we consider the preconditioning part and the DAX part, so this part is can be parallelized, very straightforward way. Okay? And you can see, so we have this global vector, and each part is on the each process. And you can see, so this type of the computation is just for the each component of the vector. Okay, so we can do this type of the computations in totally parallel manner. And this is a dot product, and we have already done in the this morning, and so we can use MPI reduce or MPI all reduce. So using the collective communication, we can do this type of the computations and communication. So next one is matrix vector multiply, and values at external points should be imported. So we need a point-to-point communication here. Okay, so this is a original global matrix for this problem. And so you can see, so we have a local matrix like this. Okay, this way. And so according to the actual numbering, so matrix itself is a rectangular like this. And this is a vectors. And the result is only for the internal nodes like this. Okay, so what is the point-to-point communications? And correctly communications are communication with all processes in the communicator. And point-to-point is a communication with limited processes, so such as neighbors. Okay? And this one occurs, correctly communication occurs mainly in the dot product or something like that in our case. And the point-to-point occurs at some communication at the domain boundary or matrix vector multiply. Okay, so this is a very simple figure to describe the features of the point-to-point communications and also finite element method. Okay, so each white circle can be considered as each mesh point, or also you can consider this as a processor. Okay, so anyway, so finite element is based on the local operations. Okay, so everything is done on elements. Okay, therefore we have a very small interactions with neighbors. Okay, and just neighbors. And so that's why we have a sparse matrices. Okay, so yeah, this figure shows the features of such kind of the applications. So therefore, if we apply the parallel computing, main part of the communication is just with neighbors. Okay. Okay, so this is again the 1D case was a point-to-point communications. Okay, so I'll talk about briefly about the method for the point-to-point communications. So we have a functions MPI send and MPI receive, RECV. But these are blocking functions, and deadlock occurs for these blocking functions. Okay? A blocking MPI call means that the program execution will be suspended until the message buffer is safe to use. So actually, when the MPI forum started to design such a library, actually, this is the first experiences for us, and they started to design the library or this interface very carefully, okay, and in order to keep the secure communications, okay. The MPI standards specify that the blocking send or receive does not return until the send buffer is safe to reuse or MPI send, or the receive buffer is ready to use for MPI receive. And the blocking communication confirms secure communication, but it is very inconvenient and impractical. And please just remember that there are such functions. So by these reasons, MPI send and MPI receive are too secure, and it's very inconvenient to for the practical use. So generally, we don't use these functions, okay? Even it's MPI send and MPI receive. I will show you how this happens, okay? For example, we have two parts here, okay? And boundary node is sending to this external node, and this one is going to this one. Okay, so we are exchanging the boundary information for matrix vector multiply, for example. So I just skipped the many arguments here, and But anyway, so if my rank is equal to 0, so neighbor is number 1. If I am 1, neighbor is 0. Okay? And call MPI send and so neighbor ID, and also call MPI receive neighbor ID. So this is something like we are sending the information to the neighbors. And so for example, this one. And also we are receiving information from the neighbors. And this seems reasonable, but stops at MPI send and MPI receive. But, actually, so sometimes it works, so according to the implementation. But if the MPI is developed strictly based on the MPI's specification, so this doesn't work. Okay. Sending 0 to 1 does not terminate until receiving at 1 from 0 is done. Okay. So, for example, so this is sending. Okay. But this does not terminate until, so yeah, this receiving is not done. But on the contrast, sending 1 to 0 also does not terminate if receiving at so 0 from 0, 0 from 1 is not done. So process 0 and process 1 so simultaneously try to send, but so they don't terminate until the receiving is so terminated. So if you see the code, so both are sending, but the next line is not coming because so yeah, you can see. So the opposite part is also sending. Okay, so this receiving does not come in this case. So usually, if you write this type of code, it doesn't work. For example, this works. Okay, so 0 is sending and receiving, and 1 is sending and receiving. Okay, and okay, so this doesn't work. So in this case, both of P0 and P1 are sending, and the sending does not terminate if receiving at destination is not completed. And both of P0 and P1 are waiting for completion of the receiving after sending. So process is stopped in this case. Okay. But this works. Okay. So if my rank equals 0, sending and receiving. Okay. And if my rank is equal to 1, receiving and sending. So in that case, so sending from 0 and receiving at 1 is so coming together, and this works. But you can see, so this is very complicated, and it's not practical. If your application is a structured message, such as a finite difference, so in that case, we have a fixed number of the neighbors and a fixed number of the parts are sending and receiving. So in that case, we can utilize this type of the MPI send and MPI receive. But it's a very exceptional case. In the case of the finite element, it's very unstructured. So in that case, so this is impossible. So we cannot apply MPI send or MPI receive. So in order to avoid this, we have another type of the communication. So it's a non-blocking functions. So it's a MPI I send and I receive. So together with MPI wait all for synchronization and termination. And also we have a MPI send receive function, but it's also limited use. And in this class, we are using MPI I send, I receive, and wait all. Okay. So basically, MPI I send and I receive, they are non-blocking functions, and they don't wait until the receiving part is terminated. Okay. But in order to keep the consistency and terminate the sending and receiving. So we need to call wait all for both for I send and I receive. Okay. So generally, so we use this way. Okay, sending, receiving, and calling wait all for I receive, then calling wait MPI wait all for sending. So actually, so we can combine these two MPI wait all for the I send and I receive. But I'll talk about that later. Okay. So, but anyway, so you need to call MPI wait all if you use this non-blocking point-to-point communication, MPI I send and I receive. But anyway, so we use this one in this class. Okay, so this is the definition of the MPI I send. So capability of the MPI I send is that begins a non-blocking send. Okay, not do a communication. It's just initiate. Okay, so send the contents of sending buffer. So starting from send buffer, number of messages count to destination with tag. And the contents of sending buffer cannot be modified before calling corresponding MPI wait all. Okay. So sending buffer is, so you are already familiar with, it's a starting address of the sending buffer. So it's something like a scalar or array. Count is a number of elements in sending buffer. So it's a message size. So data type is so integer or double precision or something like that. So destination is a rank of the destination. So it's a receiving rank ID. So tag is a, so yeah, it's a something like label. So if you are doing the, so sending and receiving simultaneously many times, so tag is used for recognize the so pair of the sending and receiving. But in this class, we don't need this type of tag. So therefore, tag is set to 0, okay, in this class. Communicator is also needed. And the last one is a very special array, so request. So it's called communication request array, so used in wait all, okay. And the important point is the contents of the sending buffer cannot be modified before calling corresponding MPI wait all. Okay, so MPI wait all terminates the sending part, but if you change so this contents of send buffer before calling the MPI wait all, that means so wrong information could be sent to the neighbors. So in order to avoid that, so we don't change the content of the sending buffer before calling MPI wait all. Okay, so request is a communication request. And so this is an array. Okay, and the size of the array is the total number of the neighboring processes. Okay, just define the array, and so I'll talk about this, how to use this in the later stage. Okay. Basically, we don't need to know the inside of this. If some error happens, so we can analyze the content of this array, but usually we don't do this. So next part is I receive. Okay, so yeah, this part is begin the non-blocking receive. Okay, you're also doing the same way for the receiving and receiving buffer and the count, data type, source, and tag, and the communication communicator, and also communication request for so receiving. And the important feature is the contents of the receiving buffer cannot be used before calling corresponding MPI wait all. This is because the before calling the MPI wait all, the receiving itself is not terminated. Okay, so that means so contents of the receive buffer might not be proper ones. Okay, and in order to use the proper value of the receiving buffer, you need to call MPI wait all before that. Okay, so that's so very important to calling the MPI wait all. Okay, so next one is the MPI wait all, and the MPI wait all blocks until all communications associated with request in the array complete. Okay, and it is used to terminate MPI I send and I receive. Okay, so at sending phase, contents of sending buffer cannot be modified before calling corresponding MPI wait all, as I mentioned. And at receiving phase, so contents of receiving buffer cannot be used before calling so proper MPI wait all. Okay. And the MPI I send and MPI I receive can be synchronized simultaneously with a single MPI wait all if it is consistent. In that case, same request, so request array should be used in MPI I send and MPI I receive. Its operation is similar to that of MPI barrier, okay? But MPI wait all cannot be replaced by MPI barrier, okay? Because it terminates the MPI I send and I receive. And if you do that, so yeah, something wrong happens. And please keep this combination of the MPI I send, I receive, and wait all, okay? So actually, the argument of the MPI wait all are so very small. Count is the number of processes to be synchronized. So this means the number of neighbors, okay? And the request is a communication request used in the MPI I send and I receive. So you need to specify the same name, okay? And another argument is the status. It's an array of status object, okay? And the size of the, so this status array is an MPI status size, which is defined in MPI f.h and MPI.h. And yeah, this is also important for analyzing the errors, but usually we don't use this. Okay, so just allocate the arrays with a proper size. Okay, so yeah, status is called the array of status object. Okay. Okay, so this is how we use the MPI I send and MPI I receive. Okay. So this is a so-called sending buffer. Okay, and we have several neighbors. Okay, and we can specify the starting point. This is a so-called sending buffer. Okay, and then we send the continuous number of the some data to the neighbors. So this is a loop for the neighbors, and so tag is equal to 0 here. So ISE and IEE is a starting point and ending point. And the buffer length, E is a message size, it's a difference between these two values. So this is a typical usage of the MPI I send. So MPI I send and the send buffer ISE. So ISE is a starting point. Okay, so it's a starting point, starting address of the sending buffer. So buffer length is a message count. MPIW is a type, and naive PE, naive is this is a destination. Okay, and the 0 is a tag, and the MPI common word. Okay, and the next one is a request to send. So this is a corresponding neighbor address. So yeah, we usually use request send in this way. Okay, the size is neighbors, and we just specify here like this way. That's it. Then we call MPI wait all after that. Okay, and so this is a number of the neighbors, and just put the name of the request send and the status send. Okay, so that is the sending part. So another part is the receiving part. And so here, instead of export, we define the name of this index as an import index. Okay, and the ISI to IEI, and the buffer length I is a message size for receiving. Okay, so this is a starting point, and this is a message size, and double operations. So this is a source, and this is a tag, and the MPI convert, and also corresponding component of the request receive. Okay, for this neighbors. And finally, we call this MPI wait for receiving. So this is a very typical way for the using the I receive, I send, and also wait all. Okay. So I'll talk about the more detail in the later stage of today. Okay. So any questions at this point? I forgot to start the. Okay. Oops. Yeah, same things happens. So, okay, I cut the WebEx. Okay. Okay, so another function is a MPI send receive. So this can do the send and receive in one function. So in this case, we don't need wait all. Okay, and yeah, it's a little bit easier, but we have many arguments. Okay, so it's doubled. But so in the case of the finite element, it's necessarily the good method, and yeah, we don't use in this class. But yeah, you may know, so this type of function exists. Okay, so this is for a little bit more complicated case. It's a 2D finite element, and so you can see. So this is a local data for one finite element case. And these are the neighbors. And you can see, so these blue part and this red part are external nodes for this process too. And you can see, so this one and this one, so they are the corresponding boundary nodes from the sending part. Okay. So basically, so receiving part is a receiving to the external nodes. Okay. So receiving the values to the external nodes. So this is happened here. So using and the sending part is a sending from boundary nodes. Okay, so you can see. So these are the external node, and this process 2 is sending the boundary nodes to the neighbors. Okay. So basically, send continuous data to the send buffer of the neighbors. And I forgot to say in the previous page, receiving is continuous data to the receiving buffer from neighbors. Okay. So this is a request and status in C language. And it's a little bit complicated, more complicated than the Fortran case. Actually, we are now using some configurations for the Fortran 77 or Fortran 90. But Fortran 23, 2003 or 2008 configuration is almost yeah, same complexity. Okay. But anyway, so yeah, you see, so in the MPI I send and I receive, we need request. Okay, and with all, we need both of the request and status. And in the C language, so they have a very special type. Okay, so this status is the MPI status, and the MPI request is for the request part. Okay, so instead of integer or so real or so single, so we have this type of the type. And this is how we define the size. Okay, you can see so status size is size of MPI status multiplied by 9p dot. Okay, and the request send is a size of MPI request multiplied by 9p dot. So this is how to define these arrays. Okay, I skip this part. Okay, so you can copy the files to your directory. So it's in the s2f.tar or s2c.tar. And please copy these files to your directory. And if you apply this tar xv, f for these two archive, so you can get the MPI s2 directory. Okay, and so this part, our codes are included in s2. Okay, so please do this. So okay. So if you copy the files, so let's start the first examples. Okay. First example is very simple program, and we have two processes, and it exchanges one value. Okay, value is a scalar, and it's a real and 8 byte, and between process 0 and process 1. Okay, so this is the procedures, and if my rank is equal 0, neighbor is 1. My rank is equal 1, neighbor is 1. And so we are sending the bar to the neighbors, okay? And the request sends 0, okay? And we receive the values, bar temp from the neighbors, okay? Like this way. Then wait all for the receiving and wait all for sending. Then var is equal to var temp. That we can exchange the value. Yeah, because so some restriction of the I send and I receive, we need to apply the different name for sending part and the receiving part. Okay, so that's why we have a different name here. Okay. Anyway, so thus we can exchange the program values. So you can see this code in S2 directory ex11.c. Okay, and you can compile this code and submit this result. Okay, so I just show you how to run this code. Okay, so if you go to the S2 and so module ex11.c. Okay, And we have a go-to.sh. So this is for the one node and two processes. And you can see, so this should be GT17, okay? Then you can submit the code. Okay, and so the output is name is test.list. Yes, this is a result. So this is the value of the scalar, and this is the number one process, and this is number zero process. So before I send I receive, the value is 10 at process 0, and it's 11 at process 1. But after exchanging, so it's 10 after this process 1, and 11 at process 0. So it's replaced and exchanged. Okay. So using the way what I showed. Okay, so I just describe the more details. Okay, so here bar and bar x are the double operations. And you can see, so start send, start receive, request send, request receiver. So these are the type, MPI status and MPI request. Okay, and we call MPI init, com size, and com rank. And we allocate the start send, start receive, and request send and request receive. So in this case, we have only one neighbor. So this part is just one, okay? And if my rank equals 0, neighbor is 1, and value is 10, okay? And if my rank is equal to 1, neighbor is 0, and the value is 11. Okay, so we start from MPI I send, okay? So sending buffer is var, size is 1, MPI double, so destination is neighbor. So tag is 0, okay? And so MPI convert and request send 0 because we have only one neighbors, and so we just apply the first component. So this case, tag is 0. So the tag values must be identical in order to exchange the information. But in this case, in this class, so every communication, the tag is 0 and it's assured. And this part is I receive, okay? And you can see we are receiving the value neighbors. And the name of the variable is value x. And the rest is almost same. So except this request receive, okay? Because you can see, so we are now sending the value, okay? And we still sending. So sending is not terminated. So therefore, if we put var here, so we may have a wrong communication. So that's why we change the name. Okay. So after that, so we call MPI wait all for receiving a part and sending a part. Okay. Then we put the value of var x into var. So thus, the exchange terminated. Yeah, this is very simple. Okay. This is the go-to.sh. And okay, so let's do some exercise. Okay. So this case is also two processes and exchanging the vector. In this case, vector, not the scalar, between two processes. Okay. So each process has a vector, so which length is 36. Okay, and so yeah, this is starting from 1, and in the case of the process 0 to process 1, process 0 send the first 11 components to the neighbors. And the process 1 receives that 11 components as the last 11 components of the original one. Okay. For the process 1 to 0, process 1 sends the first 25 components to the neighbors. And the process 0 receives the latter 25 components. Okay. So Prax is a developer program for these operations. Process 0 is sending this blue part. Okay. And this blue part is replaced with this part. And the process 1 is sending this 25 components, and this part is replaced with this part. So let's think the value of the process 0 is 101 to 136. Okay. On the contrast, this one is 201 to 236. Okay. And confirm the result in the next page, and using MPI I send and I receive and wait all. Okay, so this is a result. Okay. And this is a process 0, and this is a process 1. So you can see, so this is a starting point 101 to 136, and 201 to 236. Okay. And you can see, so for the process 1, after the 12th, it changed 201 to 225. So beginning 25 components of this process 1 is copied to here, okay, and replaced with the original one. So as for this case, you can see, so it's same up to the 225, but the 101 to 111 after so this 26. So these are first 11 components. These are first 11 components are coming to here. So please simulate or just realize these operations using the MPI I send and I receive. So this is one simple way. Okay? If my rank equals 0, so MPI I send starting from vector 0 and 11 components to request send 0, and the receiving after vector 11, 25 components like this way. On the contrast, my rank is equal to 1, so sending the arrays of the 25 components to the neighbors, and then receive 11 from the neighbors. So you can see the sending side here and the receiving side here is the same. And also sending side here from 1 to 0 is the same as receiving from 1 to 0. Okay. And then call MPI wait all. So it works. But it's complicated operations and not looks like the SPMD and not portable. Yeah, you can do this way, but I recommend you to do this way. Okay. Yeah, before calling this MPI I send and I receive, so you just specify the neighbors, starting point, so sending buffer length, and starting point for receive, and so length for the receiving buffer. Okay, then you can just specify that these name of the variables. Yeah, in the previous page, you need to specify the number, and it's not portable. Okay, so it's just for this problem. I'm not sure, so this type of application can be applicable for other type of the applications, but so this is more so SPMD like so style. And I recommend to adopt this way. Okay. Okay, so let's do this. And so yeah, please make sure that the relationship of the sending and receiving. Okay. Yeah, for example, so you can see, so we are writing I send, I receive, I send, I receive here. But yeah, if you see this, so but it's obvious. So if I send, so number 0 is sending to number 1, and the number 1 is sending to number 0. Okay, so this means, so of course, number 0 is not receiving from number 0. Okay, so this one is receiving from the neighbors. Okay, so that means, so length send and length receive must be consistent between these two and these two, not these two. Okay, so yeah, from that point of view, so this is very obvious, and yeah, you can see size of the message is different from sending and receiving here. But sending from here to here is the same, and receiving from this one is same. So yeah, please be careful about the message size. Okay. Okay, so let's do this exercise. Okay. Oh, now it's time is okay. Okay, so let's have a okay, so it's okay, so anyway, so please start the exercise. And also you can take a break. And so let's restart the class in 3:50, okay, 20 minutes from now. Okay. So this is the home page, and oops. So this is the exercise 1 for the photon and the sheet. So you can find the sample program, okay? And I just explain according to that. Okay, so this is the definition of the program. And so you can find the sample code at this directory, work GT00, these 30088 PFM answer P1. So both of the Fortran code and C code are so included here. And copy them to your directory, okay, to your, so this S2 directory. Okay, so you can see this file later, and so I just show you so what is going on. So this is a sending and receiving, and this is a examples, okay? And we start from the so defining many variables and calling MPI init, com size, and com run. And in this case, we have only processes, okay? And this is a start send, and so starting address is 1, but actually, so this is 0 in the case of the C, okay? So anyway, so if my rank equals 0, neighbor is 1, length send is 11, and length receive is 25. And we define the so value of the so vec like this way, okay? And in the case of the my rank equal 1, length send is 25 and length receive is 11. Okay, so you can see receiving length for process 0 and sending size of the process 1 is the same. Okay, and we define the content of the vector like this way. Okay. And the start receiving is a 1 plus length send. Okay. And we define the start send and receive and request send and receive. And before exchanging, we write the initial contents of the vectors. Okay, so we just write the MPI I send and I receive and wait all here. Okay. And the starting point is so it starts from 1. So therefore, starting address is -1. Okay. And also receiving address is -1 because so everything is starting with 0. So you just specify the length send MPI dub neighbor 0 is tag MPI convert and request send 0. So it's a corresponding component of the request send for this neighbor. And we are doing the same thing for the I receive. And calling MPI wait all for sending. Sending is this red and receiving is this blue. Okay. And you can see we have only one neighbor for each case. So therefore this number of neighbors is 1. And finally, we write the content of the arrays. So this is a result. Okay. Okay, so you can try this code. Yeah, actually, I'm now in this part, and so this is the x2a.c is a target code in the case of the C program. x2a.c. Okay, and go to.sh, and it's a lecture 70 and GT 17. Okay, and submit the go-to.sh. Okay, and the test.list is this way. So it's very hard to recognize, but yeah, you can see that the value is correct. Okay. So this is before, and you can see if you see the after one, this is the process 1. And mostly they are same as before, but after 26, it is going from 101 to 111. And the process 0, you can see, so the beginning 11 components are same as before, but you can see after 12, it's starting, so 201 and continuously going to 225. Okay, so it's properly exchanged as we expected. Okay, so this is a result of this exercise. Okay, so any questions? Okay, so yeah, so I have one suggestion because so the schedule is a little bit defined behind, but so we need to finish this part today. So this means so we need to make some extra 10 or 15 minutes after 5 o'clock. So is that okay for you? Yes, yeah, I'm very sorry for that. So it's a little bit late than I expected. Okay. Yeah, very sorry about that. But anyway, in order to keep the schedule, it's very essential. Okay. Okay. Let's go to the next part. So next part is actually the key part of this class, and And here, so we introduced a 2D geometry. But this one is a finite difference case. And you can see, so everything is so stored in cell center. In the case of the finite element, it's a little bit complicated. We have both of the element and node. But in this case, so everything is stored in cell center. It's based on the so-called 5-point stencil or 5-point central difference. So this is the Poisson's equations. Okay. So in this case, the discretization is like this way. Okay. So you remember, so this is second order differentiations in x direction and y direction. Okay. So this is numbering starting from 1 to 64. And we consider the decomposition into 4 parts like this way. Okay, blue, pink, yellow, and green. And this is 4 domains. Okay. And so this is a local number. Okay. And so it's starting on 1 in this case. So basically, in the case of the C, it's starting on 0. But you can define this type of the local ID. Okay, so for example, this number 16 or number 4 in the green, so they are connected to they are on the boundary, and they are connected to the so-called external partitions. Okay, and so yeah, we have some these connection to the external points for the overlapped regions. So this is the same situation as we experienced in the parallel finite element. Okay, so this is a local ID from 1 to 16, and this is a global ID. Okay, and sorry, I think, yeah, and so these are the communication between among 4 domains. And we need external nodes or external points like this way. Okay. And we have some communications. So this is corresponding to the boundary nodes, and they are exported to this external node here. And the same thing happens from here to here, or here to here. And also we have this type of the communications. So anyway, if you like to do these computations, we need some communications at overlapped regions. Okay, so let's think about the problem setting. So this is a 2D finite difference, and with 64 meshes. And each mesh has a global ID from 1 to 64. So in this example, so this global ID is considered as a dependent variable, such as temperature, pressure, etc. And it's something like a computed result. Because it's very easy to understand and easy to recognize the computations or communications are correct or not. So therefore, we specify these numbers as something like independent variables. Okay. Okay. So we have 4 subdomains, and the information of the external points is received from neighbors. Okay. And you need to consider this type of the local data structures, including external nodes. And for example, if you consider this blue part, this part and this part are corresponding to the external nodes. And this process 0 receives this part and this part. Okay. And so, yeah, in the case of this internal node, so there are no interaction with the external part. But if it's on the boundary, so you can see we should consider the interaction with the external nodes. On each process, information of internal points from 1 to 16 are read from the distributed local data. And the information of the boundary points are sent to neighbors, and they are received as information of the external points. So what we are trying to do is, so initially, so we have this kind of the data, okay? So basically, so we have 24 meshes in each local data, but only value of the internal nodes are stored, okay, like this way, 33, 34, or something like that. And after 17th, so these external nodes are not included. But what we are trying to do is doing the communications between neighbors, and they get the information of the external node from the neighbors, okay, like this way, okay. So this is a target result which we are now aiming, okay? And we try to design the data structure and also the program for that, okay. Does it make sense? It's a very simple way, but not so easy, okay. But if you provide a sophisticated data structure or proper data structure, it's not so difficult. And you can extend that idea to the parallel finite element very easily. Okay, so let's go ahead about the distributed local data and communication table. Okay, so let's think about this process 0. Okay, so this is a value at each mesh, and it's a global ID. And this is a local ID, okay, 1 to 16. And this is a very typical SPMD computations. And so we are running the 4 processes. And we have 2 types of data. Okay, one is SQM dot 0 to 3, and another one is SQ dot 0 to 3. Okay, so SQM dot 0 to 3 is a distributed local data sets, including neighbors, communication tables. And another one, SQ.0 is it's also the distributed local data set, but a global ID of internal points are stored. So you can see, so this part is corresponding to geometry, and this one is for the results, okay? Okay, next, we'll discuss about some information at each partition. So internal points are meshes originally assigned to the domain, okay? And the external points are meshes originally assigned to the different domain, but required for computation of meshes in the domain in the boundary, okay? And this part, so these external points are sometimes called sleeves or halo, okay? So halo is this type of some rings around the sun, okay? So you may have seen about some very old European medieval painting. So in the angels, so angels have some rings on the top of the head. So that is also called halo. Okay. And in Japan, we call this part sleeves. So it's something like sleeves. But in Europe and USA, so they call this part halo. But anyway, so this external point is very important for the this type of the parallel computing. And boundary points are internal points, which are also external points of the other domains, and are used in the computation of the meshes in other domains. So basically, you can see, boundary points are the neighbors of the, are connected to the external points like this way, okay? And the relationship between domains, so that is called communication table. And external points and boundary points and neighbors. So as I mentioned, numbering starting from internal points, then external points after that. So like this way, okay? So 1 to 16 and 17 to 20 and 21 to 24, okay? So neighbors are share the overlapped meshes, and we need a number and ID of the neighbors for the information. Okay. And the import table is for the receiving. This is from where, how many, and which external points are received or imported. So this import table is related to the external point. Okay. On the contrast, we have an export table for sending. So this is to where, how many, and which boundary points are sent and exported. So this export table or sending table is for the boundary nodes. Okay. So in this case, you can see numbering for the external nodes for the each neighbor is continuous within each part. So this is very important features. And so I will talk about that later. But yeah, please keep in mind that numbering is continuous in each neighbor. Okay. Okay. So this is a numbering. Okay. So next one is a generalized communication table. So it's a sending part. Okay. And so we have several informations. So one is a neighbors. Okay. So naive p dot is the total number of neighbors. And this naive p is the size is a naive p dot. It's the ID of neighbor. Okay. And the message size for each neighbor is an export index, and the size is a naive p dot plus 1. And the ID of boundary points. Okay. So this is a export item. And the size is the export item naive p dot. And the message to each neighbor is a send buff, and the size is the export index naive p dot. So relationship between export index, export item, and send buffer is that of the index and item and emat in the CRS format. Okay? And it's very similar relationship. Okay. So this export index provides a accumulated number of the messages in the export table in each neighbors. And so this one is corresponding to the each component for the node ID, and this one is a value of the at each boundary node. Okay. So you remember this figure which is used for the sending, and before sending the values, so we copy the values at boundary nodes to the sending buffer, okay, using this export index and export item. Okay. So you can see, this is a groups for the neighbors, and the export index is a starting point for the values. Then, this value is copied to the sending buffer. So actually, so this sending buffer is a continuous array like this. But a boundary node, so numbering is not necessarily continuous. So in order to utilize the features of the MPI, so we use this type of the sending buffer. So I'll talk about that later more in detail. Okay, so this is a structure of the generalized communication table for receiving. Okay, and it's almost same as for the sending, but so we have a different name. Again, we need information about the neighbors, so number of neighbors and ID of neighbor. So it's shared with the sending part. And the message size for each neighbor is import index. And the ID of the external points are defined as an import item. And the message from each neighbor is a receiving buffer. Okay, so like this way. So this is how we utilize receiving. And so we receive the continuous value of the receiving buffer and call wait on for receiving. Okay, so after that, so we can copy the value of the receiving buffer to the value at the external point. Okay, so using this import item. Okay. So as I mentioned in the previous part, relationship for the sending and the receiving is very complicated, and also it's very important to understand that. And consistency of IDs of source and destination, size and contents of messages. So yeah, this is very critical point. And if we have some problems for these, okay, some inconsistency, the communication don't go properly, okay? And the communication occurs when neighbor number, neighbor ID is matches. So actually, so the tag is always 0, and so if this neighbor's ID are matches, we have a communication. For example, so this is a number 0, and this is a number 3. And so number 1, 3, 5, 9 are neighbors of this number 0, and number 1, number 0, and number 10 are the neighbor of the receive 3. So this is a list of the neighbors, 1, 3, 5, 9. And this one is 1, 0, 10. Okay. So if this neighbor ID is matches to each other, the communication occurs between these two. So in that case, so message size must be identical for sending part and receiving part. And the sending part from here to receiving part. Okay, so let's make the generalized communication table. Okay. So here I show you the actual examples, and you can understand more clearly by this example. So this is process 0, and you can see 1 to 16 is internal points, and we have 2 neighbors and totally 8 external points. Okay. The first part is neighbors, and total number of neighbors is 2. Okay, so because we have 2 neighbors, so this one is 2. So next part is a list of naive PE. So it's an ID of neighbors. So process 1 and process 2 are the neighbors here. So next part is node. So we have 2 numbers here, 24 and 16. And the latter one, 16 means number of the internal points. Okay, and the 24 means all number of nodes. Okay, so that 24 minus 16. So difference between these numbers are number of the external nodes. Okay. Okay. Does it make sense? And the next part, so I'm describing the import index. Okay. So you can see here we have two numbers at import index. So this is corresponding to we have two neighbors. Okay. And so this means so first four export external points are imported from first neighbors. First neighbor is this process one. And 8 minus 4 is 4. And the next four so items, so fifth to eighth are from the second neighbors. So this is the accumulated numbers. And totally we have 8 external points. Okay, so this 8 is corresponding to we have 8 external points. Okay, so this is the same rule as we did in the CRS format in the sparse matrix. And so first 4 are from the first neighbors. So next 4, 8 minus 4 are from the second neighbors. Okay, does it make sense? Okay. And the next, we have a list of the import items. Okay, and you can see, so we have 8 components here. Okay, and the first 8 items, so 17 to 20, so they are imported from the first neighbors, process 1. And the 5th to 8th, so they are imported from the second neighbor, number 2. So that's very simple data structure. Okay. So next part is a export part. So here we also have the 2 numbers here. So that is corresponding to we have 2 neighbors. And in this case, we have totally 8 boundary points, and the first 4 is going to the first neighbors, and the next 4 is going to the second neighbors. And we have a list here, and 4, 8, 12, 16. So these 4s are going to the first neighbors. And the 13, 14, 15, 16, so they are going to the second neighbors. And the external point is only sent from its original domain. But the boundary point could be referred from more than one domain. So and sent to multiple domains, like this way. Okay. So actually, here, this number 16 is sent to both neighbors. Okay. But actually, we have only 7 boundary points, but we count as 8 because it's duplicated. Okay. Okay, so this is same figures. Okay, so this is features and a very brief overview of this data structure. Any questions so far? Okay, so let's go to the next part. So you can see SQSR1.f and SQSR1.c. So you can find the code which is doing this computation and communication, mainly for communication. And we are using the 4 processes, and please modify this go4.sh and run the code. Okay. But anyway, so I just go into the details. Okay. So this is the go4.sh. And please don't forget modifying this resource group and this group name. Okay, so this is the beginning part of the SQSR.C. Okay, so we have several node variables and arrays here, and so yeah, we need to define some arrays like the import index, export index, import item, or export item. Okay, we call MPI init, com size, and com rank. And then we read the SQM dot something. So this is a mesh file. Okay, and so we are opening this file and reading the information. So this part is corresponding to the each part of this data which I just mentioned. Okay, so actually, so we are reading this header, but so we skip that part to save the space. Okay, first we read the naive p dot here, like this. In this case, it's 2. And we allocate the naive p, size is the naive p dot. And we also allocate the import index and the export index. So size is 1 plus naive p dot. Okay. And the next, we read the list of this neighbors. They are stored in the naive p. So next, we read the node number. NP is all meshes, and N is internal meshes. Okay. In the next part, so we read the import index. So import index 0 is 0, and import index 1 and 2 are red. So you can see this is a naive p dot. Okay. And NN is equal to the import index naive p dot. So this is corresponding to this 8. And this is a number of import items. And it's allocated as this way. And we read the content of the import item. Okay. Yeah, we are reading here. Okay. So next part is reading the export index. And we do the same operations as we did in the import part. Okay. And NN is the export index naive p dot. It's the size of the export item. And we allocate export item and read the value. Yeah, in this way. Okay, next part, we read the SQ dot 023. So they are storing the information. So this global ID for internal nodes. Okay. And so var is arrays for these values, but please make sure that the size is NP, not N. Okay, because we need a value for the external nodes. But here we just read just for the internal nodes. You can see group is from 0 to N. And at this stage, so the values at the external nodes are empty. Okay, and these values are imported from the neighbors by communication. Okay, using the generalized communication table. Okay, so this is how we do the communication. Okay, so we just allocate the send buff and the receive buffer. Okay, and so size of the send buffer and receive buffer is same as the export item and import item, and the size is the export index naive p dot, and import index naive p dot. Okay. So before communication, we copy the values at boundary point to the sending buffer. So this is a process. Okay. So you can see, so this is a loop for neighbors, and I start and I send. So this is some index for the boundary node. Okay, and from I start to I end is a loop, and the export item is the ID of the boundary node, and the value at the boundary nodes are copied to the corresponding address of the sending buffer. Okay, so information of boundary point is written into sending buffer, send buffer. Information sent to naive PE is stored in send buffer export index naive to export index naive 1 plus 1 minus 1. Okay, so here. Yeah, because so this sending buffer is very important because you can see these boundary nodes are not necessarily the continuous numbering. And we cannot directly send this information to the neighbors using MPI function. Okay, so in order to do that, so we need to introduce a sending buffer. So in the case of the receiving buffer, okay, this external point, somehow we can make some continuous numbering for each neighbor like this way. So in that case, we don't need to care about that. Okay, so anyway, so this type of the sending buffer is very important for the sending part. Yeah, this is a communication pattern. So using the 1D case. So this is a provided by my very old friend. So he's working for Lawrence Berkeley National Laboratory. Okay. So you can see, so he mentioned this part as halo. Okay. And this is a external nodes, and this is an internal node. And you can see, so you are collecting the value of the boundary nodes. So you can see it's scattered, so it's not continuous. And it's stored in the continuous buffer. It's a send buffer, and they are sent to the neighbors. And this part is also sent to the neighbors. And they receive. Okay, it's a receiving buffer. And so receiving buffer value is a copy to the halo. But you can see, so values are continuous, okay, for each neighbor. So that's why this process is, this receiving process is done more smoothly. But in the case of this sending part, so you need to make the continuous buffer. Okay. So after that, so we define the start send and receive and the request send and receive. And based on the MPI status and MPI request and the number of neighbors, so we can allocate these arrays. And the first part is sending. Okay, so this is a loop for the neighbors, and we specify the starting point and ending point by export index this way. And the buffer length is message size is a difference between IN and I start using this export index. The sending message to this neighbor is a send buff. I start is the starting point, and the buffer length is the message size. So in this case, it's an integer, MPI int. And this is a destination, and the tag is 0, and the MPI convert, and the corresponding component of the request send. So this is the MPI I send. Okay. Okay, so basically, so we are starting from this side. Okay, and so you remember these figures, and so if it's more clear, okay, and this is a so final sending buffer. It's continuous, you can see. Okay, and this part we are sending this information using MPI send. So before that, we need to copy the value at boundary points to the sending buffer. Okay, so you can see this k is continuous. Okay, but this kk is not necessarily continuous. So yeah, we have a continuous array to utilize this MPI function. Okay. Okay, so next part is receiving. Okay, it's same as sending, and here we are using import index and import items. Okay. And so this is a receiving buffer, and I start is a starting point, and the buffer length is a so message size. So MPI int and neighbors tag is 0, MPI convert, and the corresponding component of the request receive. So this is how we call the MPI I receive. Okay, we are doing these import items now, and so this is a receiving part. So first, we receive the information as I mentioned in the previous page, and so after that, so we call MPI wait all. After that, so we can utilize the content of the receiving buffer. And here we are copying the content of the receiving buffer to the this value at the external point. Okay. Yeah. So this is the copying part. So because we are calling the this wait all for receiving first, then we call we are copying the values at the external point, then call the wait all for sending. Yeah, actually, so we can put this part before, but so anyway, so uh, anywhere you can put this one. And finally, so we output the values for each node. Okay, so that's the procedure. Okay, so this is the writing part. And this is a result. And so you can see each output, they are writing the value of the external node in the sequence of its number. For example, this number 0 is receiving 5, 13, 21, 29 from first neighbor. So it's a process 1. And from the second neighbor, process 2, so it's receiving 33 to 36. Okay. So it's also same for this one. And process 1, so neighbors are number 0 and number 3. So we are receiving 4, 12, 20, 28 from number 0. And 37 to 40 are received from number 3. And this is for the number 2 process and the number 3 process. Okay. Okay, so you can just run the code and so see what is happening. Okay. Oops, it's Okay, so let's go to the my directory. Oops. So, これじゃないな。Just a moment. I put the wrong file. This should be. I think that not this one. Okay. So this SQ SR1 is the correct one. Okay. And the go for.sh. Yeah, that should be 17. Okay, so it's running now. And you can see the contents. So test.list. Okay. So it's running. Okay, it's finished. And so test.list is like this way. And you can see, so you can get the same result. Yeah, for example, you can compare this process 3. Okay. And so this is results. So this is a result. And so neighbor is 2 and 1. Okay. And 36, 44, 52, 60, and 21, 31, 30, 31, 32. So they are received properly. Okay, so thus you can check the validity of the result. Okay, so any questions for this part? So actually, so this part is very important part for the designing the parallel data structures. And this is a distributed local data structures for parallel computations. And here, so this local data structure for domain-to-domain communications has been introduced. So which is appropriate for such applications with sparse quotient matrices, such as finite difference, finite element, finite volume, etc. So it's based on the SPMD, and it's based on the local numbering. So internal points first, and then external points next. And then we define the generalized communication table, import index item and export index item, and also the information about the neighbors. So actually, so everything is very easy. So if proper data structure is defined, and the values at boundary points are copied into sending buffers, and we do the sending and receiving. Then values at external points are updated through receiving buffers. So that we can easily do the parallel computation. Okay, so next part is exercise, and at this time we have 25 meshes. Okay, and let's think about dividing into 3 domains. Okay, and like this way. So this is a global numbering. Okay, and, so these white part are external nodes. Okay, And we can apply the local numbering like this way. Okay. So we have 8 internal nodes process 0, and also 8 in the process 1. And the process 2, we have 9 internal nodes. And you can see, so external numbering is like this way. So 10 to the 12, 13 to 15, like this way. So red numbers are external numbers. So this numbering is already specified. Okay? But you can see, so this geometry is much more complicated than before. So in the previous case, we have equally distributed numbers, and also number of the internal nodes and external nodes are all same. But in this case, it's a little bit different, okay? And it's more complicated. So what you have to do here in the exercise is, so you have information about a neighbor and node ID. So this is the total number of nodes for the internal node. So you specify the import index, import items, and export index and export items. Okay. So this is number 0, and this is number 1. Okay. And this is number 2. Okay. So in this case, please be careful that so sequence of the neighbor is 1 and 0. Okay. So this is very important. Okay. And these return values are already specified. And according to this information, please complete these import index items and export index items by yourself. So this is a exercise here. So actually, so my initial plan was doing this. So at the end of this day, but so actually, so we don't have enough time. So I'd like you to do this by yourself. Okay. And so this is geometries, and so this is the procedures. So how to do this? Okay. So number of internal and external points are already defined. And so where do external points come from? So it's easier to define the import index and the import items earlier. Okay. And please be careful about the sequence of the neighbors. Okay. Then check destination of the boundary points. And so we can define the export index and the export items. So again, so please be careful about the sequence of the neighbors. Oops. Okay. So SQ. So SQ dot star are already in this S2 in EX. So if you go to this EX directory, so you have already have SQ.0 to SQ.2. Okay. Like this way. Okay. And you also have the go 3.sh. So you have 3 components, 3 domains, and you can run the 3 processes. Okay. And what you have to do is create SQM.0 to 2 by yourself. And in this case, you can use the same a.out, which you created in the S2. So using the sqsr.f and sqsr.c. Then, so if the SQM dot 0 to 2 are defined properly, so the program works well. Okay. And actually, the next exercise. So this is a big exercise, and this is so parallelize the 1D code using MPI. So using this generalized communication table. Okay. So in this case, read entire element number and decompose into subdomains in your program. And so first, you should validate the result. So answer of the original code is equal to the answer of the parallel code. And so explain why number of the iterations does not change as number of MPI processes changes. Okay. So if your program is so properly developed, even if you increase the number of MPI processes, the number of the iterations for convergence doesn't change. And yeah, please explain for that. And also please measure the parallel performance. Okay. And apply the generalized communication table and read the entire. So yeah, this part is same. Okay. And evaluate the parallel performance. So actually, you need millions of elements to get the proper or reasonable parallel performance using up to 12 nodes. That means almost 600 cores. But in that case, it doesn't converge within 15 minutes if you apply the small number of nodes. So in that case, so you can fix the number of iterations. For example, it's about 100. And so let's evaluate the convergence is the same up to this point. Okay. If your code is properly coded, the answer at 100 iterations are same for the serial code and parallel code. Okay. Yeah, you can reduce the number of iterations, even if it's not converged. Okay. Yeah, so report is not specified, but you should think about these things. Okay. Okay, so these are the examples of the shell script, and so these are the some such cases. Okay, so before doing this exercise for the parallel version of the 1D code, please do this exercise, okay? Because it's very good experiences to understand the general communication table. Okay. So actually, 1996, I started to develop the parallel finite element code. Okay, so it's almost 30 years ago. Okay, and at that time, so we have already idea about this generalized communication table, but we need to confirm that this works properly. But so at that time, we didn't know MPI, okay, and we have no parallel machine at that time. And what we have to do is we have to check everything by hand, okay? And so what you are doing now is so what I did. So 27 years ago, okay? It's very good experiences for the development of the parallel algorithms. And now, so everything can be done by tools, and so you have no opportunity to think about the very fundamental part of this parallel computing. And if you have more than 100 meshes, so it's very difficult. But this case, you have only 25. Okay, so it's not so difficult. And so yeah, so you should try this before going to the 1D parallel finite element method. Okay. Okay, so thank you very much. And yeah, fortunately, so we can finish before 5 o'clock. Okay. And so if you see the schedule, so tomorrow, the first two slots are exercise, okay? And please do this exercise and also the 1D finite element. Yeah, I know the time is too short to complete the 1D parallel finite element. So, but so please try, okay? And so anyway, so you need to understand the materials today, okay? Especially for the afternoon part. And so review the materials. And from 11 o'clock, so I start to explain the sample implementation of the 1D parallel code, okay? And so yeah, hopefully, so you can understand the code so clearly by preparing for that. Okay. Okay. So thank you very much. And so I'm very sorry for some accidents. Actually, it's not my fault, but so sometimes this happens. Okay. And yeah, we are lucky because we are so in person. And yeah, this kind of sometimes happens in the remote environment, and it's very terrible. Okay. Yeah, usually I gave lectures in Japan remotely, and so yeah, several months ago, some network shutdown happened, and 10 minutes after, I go back to the Zoom, but yeah, I was very surprised. So everybody was there, okay? So they don't leave. Okay. But anyway, so I'm very sorry for that. Okay, so now it's almost 5 o'clock, and at this point, do you have any questions for the content of today or yesterday and Monday? Okay, so yeah, please try the first small exercise and then go to the big exercise. Okay, so see you tomorrow at 11 o'clock. Okay. Yeah, I'll be here so as soon as possible. Okay, as early as possible.